Let's take a look at an example problem using Bernoulli's equation and Bernoulli's principle. You blow a stream of air at 3 meters per second over the top of a 1-gram sheet of paper that measures 20 meters per side. Which way will the paper move, and what is the net force acting on the sheet? Okay, well, first things first, Bernoulli's equation and Bernoulli's principle basically say the same thing. They say the faster a fluid moves, the less pressure it exerts. Where the velocity is high, the pressure is low. Where the pressure is high, the velocity is low. So up here we actually have a high velocity. The velocity is 3 meters per second. Down here we have a low velocity. We're assuming the air down here is stationary. That's 0 meters per second. So the paper is actually going to move up, and you can try it. You can grab a sheet of paper, blow over the top of it, and you'll see that it will move up. Now, I want to know the net force that's acting on the sheet. Before we blow on it at all, you're supporting it and gravity's pulling down, and those two things they cancel out. So really all I want to know is what's the differential from the pressure that's acting on this sheet of paper. And Bernoulli's equation says P1 plus 1/2, or it depends on whatever, 1/2 rho V1 squared plus rho GH1 equals P2 plus 1/2 rho V2 squared plus rho GH2. Well, there's a couple of these that can go away right now. If this is P1 up here and this is P2 down here, or this is my one side and this is my two side, the height is the same. We don't have a height differential in our column of air, so whatever our height is, those terms will subtract off of each side and we're done. Okay, so now I'm down to P1 plus 1/2 rho V1 squared plus, just equals P2 plus 1/2 rho V2 squared. Now, there's only one thing I don't know. I know, there's a couple things I don't know. I don't know what the pressure is up here or down here, and that might be okay because I want to know the force acting on them. So I also don't know the density, but the density of air is something I can look up, and if I just do a quick search for that, the density of air is 1.29 kilograms per cubic meter, which is an incredibly low density, right? The density of water is 1,000 kilograms per cubic meter, but we should expect that air floats, so it's not a very dense thing. So here we go. Let's go ahead and start doing some things. I'm going to replace pressure with force and area. So remember, pressure is actually force over area. So this is force 1, area 1, plus 1/2 rho, which is 1.29, times V1 squared. Well, V1 I know is 3, and I'm going to square that, equals P2, which I'm going to say is F2 over A2, plus 0, because the velocity over here is 0, which really means I have F1 over A1 plus 1/2 of 1.29 times 9 equals F2 over A2. Well, if you think about that, that F2 is pushing up. It's the air down here. This is F2 pushing down. It's the air down there. And I actually know the area because it said this is 20 meters per side. So the area is equal to 20, well, except it's in centimeters, so 0.2 squared, and 0.2 squared is 0.04 square meters. So I can sub in that into my equation. So now I have F1 over 0.04 plus, and let's just go ahead and do this math, 1/2 of 1.29 times 9 is 5.805 plus 5.805 equals F2 over A2. Well, the net force acting on my sheet of paper, if we go back up and look, is equal to F1 up here and F2 down here. Those are in opposite directions. So the net force is equal to F2 minus F1. And I put them in that order because I assumed up was positive. So what I really want is F2 minus F1. So I'm going to go ahead and subtract off F1. So I have 5.805 equals F2 minus F1, and this area is the same, so 0.04. And so then I can multiply both sides by 0.04, and I get 0.232. 0.232 newtons is equal to F2 minus F1, which is the net force acting on my sheet of paper. So 0.2322 newtons. Now I want to point something out about that. That is a positive force, just like I thought it should be, because the paper was going to go up, so there's a net force up. And also, since the height didn't change, that dropped out. Now sometimes, in a column of water, say, if you had a pressure here, P1, and a pressure here, P2, according to Bernoulli's equation, and this is not moving, so the kinetic energy at both places would be the same. So this P1 plus, and the kinetic energy term I'm going to leave out, plus rho GH should equal P2 plus rho GH. Well, this H, if this is H2 and this is H1, then what we have is P1, and I'm going to actually subtract this off, minus P2, so the difference between these two things, and so this is H1 and this is H2, is equal to, and now I'm going to subtract that off, rho GH2 minus rho GH1. Well, 2 minus 1 gives me this difference in height, and so basically it tells me the difference in pressure between here is equal to, P1 minus P2 is equal to rho GH times the delta height, which is, as you recall, the density with, or the pressure with depth pressure, which just says that the pressure at a depth is given by rho GH. So Bernoulli's equation is actually kind of powerful, and since we made it general, it does a lot of things, but it's also a little bit complex. So look for times when terms cancel out.